hi everyone.
You can just take it off.
Yeah. So it's great to finally be a speaker at Spacecraft. I've been coming here for I think the last 4 years. And I've always really enjoyed the atmosphere, so now this is finally my time to do something back. So today I'll tell you a little bit about how planets form, and specifically how planets that might be habitable form. So this is very much going to be a story about rock and ice. So you can think of rock as the Earth as a rock, and then ice or water coming from space, those two coming together and forming a planet that might be habitable. That's the story I'm going to tell today. For those of you wondering about my name, by the way, I'm originally from the Netherlands. So my name is Gijs, but you can say Gijs if you want to talk to me after the talk. So planets form in protoplanetary disks. Protoplanetary disks are disks of material, dust, and gas that surround young stars when they are born. So when a star is born, some of the material that's left over from the star formation orbits that star in a disk, and that disk contains enough material to form planetary systems. Astronomers can observe these disks around other stars, around young stars specifically, and if we measure how much dust there is in these systems, there's enough dust to form planetary systems. There's enough dust to form planets like the Earth. So planet formation is basically the story of how you take the material that you have left over from star formation and you combine that, growing it into larger and larger objects that eventually will become planets. So when I talk about planet formation and when I talk about how planets form, it's basically a story of bringing together small things, making bigger things, and repeating that process into bigger and bigger things until you eventually end up with a planet. So it's starting with dust, so migrant-sized dust grains, combining those into larger and larger objects you can think of as rocks, combining those together by the gravitational pull, and eventually forming a planet. And then once you form the planet, the question is, well, what type of planet is this? Could this be a planet like the Earth? Could this planet be different? And could life develop on this planet? So, hopefully the end product of planet formation is a planet like the Earth as you see behind me, but there are also different outcomes possible. So today I'll talk a little bit about how planets form and what different outcomes you may have, and what that means for if a planet could be habitable or not. So I told you this is a story about rock and water, and basically how to bring those together to form a planet that could be habitable. I realize it's maybe a bit weird to talk about water in a brewery. So I realized that beer is actually 95% water. So every time you drink your beer, remember this is what I'm talking about. So combining rock and water to make habitable planets. So this is a nice picture showing that maybe this is the way that how Earth receives its water from space. So we think that water is crucial for whether a planet is habitable or not. A planet like the Earth, like life on Earth, cannot exist without water. We know life as we know it requires water to be able to survive. So when we think of planets that might be habitable, we're looking for planets that could also have water. And this is what when astronomers talk about habitability or habitable zones or sometimes habitable planets, they're often talking about planets that might have liquid water on their surface. So this is often called the habitable zone. Maybe you've heard of this as the Goldilocks Zone. And it basically tells you where does a planet have to be with respect to its star in order so that there can be liquid water on its surface. For example, like on Earth, we have oceans, lakes, everything. So if a planet is too close to its star, it's going to be too hot. So you get something like Venus, where all the water is in vapor in the atmosphere, and we don't consider that habitable. If a planet is too far, all the water will freeze out, it will become ice. And we don't think that's habitable either. So the distance matters a lot, like where does a planet form? The size of the planet also matters. If a planet is too big, it basically doesn't have a surface because it's a gaseous planet. So we think that large planets also are not habitable. So when I'm talking about habitable planets, I'll be talking about smaller planets. If a planet is too small, it might also not be habitable because it will actually not be able to hold on to its water. So think of Mars, which has lost a lot of its water simply because it was, or one of the reasons is because it's much smaller than Earth. So a planet needs to be the right distance from its star, and it needs to have the right size. But that's not everything. That means there could be liquid water on its surface. So then the question is, does this planet actually form with water or not? And this is something I've done a lot of research on, and what I want to talk to you about today. So this is also going to be the first pop quiz question. So how much water does Earth have? So what fraction of Earth's mass is water? Is it A, 70%, B, 6%, C, 0.5%, or D, 0.04%?
Right here. 70%. 70%? In the back. Louder.
See.
C? Right here. D. Congratulations. You get it.
That is indeed the correct answer. So it's funny to realize this because when we look at the Earth, we see clouds, we see oceans, and indeed Earth is covered by about 70% water, the ocean. But if we take all that water together and put it into a ball, it's only a very small fraction. So Earth's oceans is 0.02% of the Earth's mass. And there's probably more water on Earth than just in the oceans. There's probably some water in the mantle as well. So if you add that, you get something that's a little bit higher, so 0.04%. So that means that despite that Earth we consider it habitable because it has water, it only has a very little bit of water. Most of its mass is not in water. It's only a tiny fraction of water. So when I think of Earth as how much water it has, I think of it as a very dry planet. And not as a planet that has a lot of water. So the question is, like, how did Earth form with only very little water? And so we have to go back to these protoplanetary disks, so the regions where planets form around young stars. So again, it's a story of how far you are to the star and what type of material you may find. So if you're very close to the star, any objects you have, so your dust floating around, water can't condense in that, so water will be in vapor. They form with some water. So this is now the mechanism how we understand formation of at least something that might look like the Earth. So on a scale from very dry to very wet, the Earth is somewhere on the, I would say, on the dry side. And if you do the simulations, not just for the solar system, but also for slightly different conditions, larger planets, planets a little bit further in, further out, you get sort of a range. But in general, these planets, they always form with a little bit of water. So that's good news. So that means that we find a planet that is similar to the Earth, it will probably also have water. So that's good for habitability. But there's a caveat. So I'm not sure how many of you know this, but of course there's a lot of different stars we can see in the night sky, and not all stars are like the sun. So I wasn't allowed to do another pop quiz question, so I'm going to ask it anyway. So stars vary in size. You have very small stars, very large stars. So large stars are O stars, and the smallest stars are N stars. Does anyone know, like, the stars you see in the night sky, what type they are? Are they like really big ones, or small ones, or in between? Big? That's very good. So most of the stars you can see with the naked eye are a little bit heavier than the sun. So we call them B and A and F stars. And they're very bright, so you can easily spot them, so that's why we see them. But most of the stars, for example in the galaxy or also in the neighborhood, they're much fainter, so you don't see them, but they're actually very numerous. So most of the stars that we think are in the galaxy are basically the smaller, what we call M-dwarfs. So about 75% of the stars are much smaller than the sun. So if we're thinking about planets and where life might be in the universe, we also have to consider these very numerous stars that are not like the sun. So
So when we think of different types of stars, we also have to think of how does it change our idea of habitability. So if you have a very massive star, which is very bright, the location where planets can have liquid water on its surface also moves out. You have to be further away to reach the same temperature, basically. So if you go to these lower mass stars, what we call M-dwarfs, these stars are smaller and they're also fainter. So in order for a planet to be as warm, you have to be a little bit closer in. So that means the zone where you can have liquid water on the surface for a planet moves in. So we say the habitable zone is closer into those stars. So what if we form a planet there? What if we form a planet around a star that is much less massive than the Sun? So it's a very common star. The planet is going to be closer in, but will that planet get water as well? So I've been doing some simulations, and other people have done a lot of these simulations as well. And so it's the same simulation you've seen before. There's now 3 different panels. Again, like things on the left. Yeah, things on the left means it's close to the star and they're dry initially, so they're red. Things on the right, they start more with water, so they are blue. And then we follow the formation process of planets. And sort of the vertical purple band denotes the location where the habitable planets could be. So let's see what happens. So things are moving around a little bit. You see some of the dots change color, but not all of them do. So in these simulations, about 4 of the planets, they don't get any water at all. There's just not enough scattering going on around these low mass stars. So not all of these planets actually get water. And some of the planets do, like you see in the top left panel, there's some water being delivered to that planet. And so basically what that means, if we go back to our scale, very wet planets and very dry planets, where the Earth was sort of somewhere on the bit on the dry side, but kind of in the middle, around these M-dwarfs, we expect that these planets are much drier. Maybe they won't have any water at all, or maybe they'll have a little bit. So it's going to be, if we can find those planets, they're going to be very different. So that's interesting. Now, as I mentioned, the habitable zone is a bit closer in, which means that also the planets are closer in. And the solar system, for example, doesn't have planets that formed that close to the star. So the question is, can you actually form these planets so close in? And some people think, well, you can't do it the same way as we did for the solar system, but maybe there's another mechanism at work. So that mechanism is called planet migration. So the idea of that is you don't form a planet where you observe it now, but you form it further out in the disk. So this disk, remember, they have gas and dust in them. And the dust is what forms sort of the rocks and initially the planets, but the gas also has an effect. So if you form a planet, and then the planet and the gas interact gravitationally, what happens is the planet pulls on the gas, then the gas also pulls on the planet, and this makes the planet move. So this is a simulation where the initial location of the planet is this ring, and you see that there's this nice spiral that the planet excites, and then the planet moves a little bit inward as well. So I'll play it again. So the planet starts in the disk. You see the spiral arm developing, and then that spiral arm sort of pushes the planet inward. So a planet forms further out, and then is moved inward. And of course you can imagine this matters a lot for its composition. If you think of previously we had to get some icy material and just move it inward. Now we can just form a planet there and move it inward completely. So there's currently a discussion on whether those planets are on M stars, like how they form. Do they form like in the solar system, so they would be very dry, or do they form via this process of migration, which means they form basically very icy and then move inward. So if you go back to the scale of very dry to very wet, the other possibility is that these planets around these lower mass stars, they are extremely wet, so they have like 10 or 50% of water. So think of something as like Europa, the moon, or any of the other icy moons, or maybe something like Neptune with a lot of ice. So these are like theoretical possibilities, right? It's based on what we know of the solar system, it's based on simulations, but the big question is, of course, are these planets actually there? And we have found some, but I'm not going to talk about that, and I'll leave that to Chris later today. So thank you very much for your attention.